Yesterday we did one example of a collision that illustrated the conservation of momentum, and today we're going to look at a few other examples. Today we're going to look at the example of two objects that are separate before the collision, and then together after the collision. The major equation we're going to use is, again, the conservation of momentum, which says the total amount of momentum before has to equal the total amount of momentum afterward. In these situations, you'll have on one side a bunch of separate momentums being added together. We'll have only two, but it could be 3 or 4 or more. And afterward, you'll have one combined mass, which is just the total sum of all the masses, times one combined velocity. Here we've got a car traveling at 30 meters per second, and it collides with a bigger truck moving 20 meters per second in the opposite direction. So notice the use of a negative sign for the velocity here. After the collision, the two vehicles remain together, and we want to know how fast they move off and in what direction. I'm assuming that it's going to move off to the left, which suggests we should end up with a negative number for our speed, but we might find out that it's a positive number. Let's see what happens. The momentums before is the mass of the little car times the velocity of the car plus the mass of the truck times the velocity of the truck, and that has to equal their combined mass times their velocity combined. The mass of the car is 900 times its velocity was 30 before the collision. The mass of the truck is 3,500 times its velocity, which was negative 20 before the collision. That's 27,000 plus a negative, and 2 times 35, that'd be 70, and 3 zeros, 70,000, or a total momentum of negative 43,000 kilogram meters per second before the collision. Afterward, the combined mass was 3,500 plus 900, or 4,400 kilograms, times v. That's equal to negative 43,000, so simply divide both sides by 4,400, and we get that the velocity after the collision is equal to negative 43,000 divided by 4,400, or roughly 9.8 meters per second. It was negative, which means our assumption that it was going to keep going in the direction that the truck was going is correct. The other type of collision that we can explore is the opposite, when objects start off together and end the situation separate. An example of this, remember, is an explosion, where things start off together and then afterward lots of little pieces are heading off in different directions. Here we'll have a combined mass times its velocity, and then afterward there are separate objects, each with their own masses and velocities that must be added together. If you've ever been hunting, you've probably felt that after you shoot the gun comes back, recoils, and hits you in the shoulder. What I'd like to do is to calculate how fast that recoil is. Suppose we have a 5.7 kilogram rifle and it shoots out a bullet of 40 grams at 640 meters per second, which I understand is faster than the speed of sound, but we'll go with it anyway. What I haven't illustrated here is that before we shoot the gun and the bullet are actually one object that has some momentum. Well, actually it has no momentum because you're probably holding the gun still, so it's not moving. So before the collision, we have the total mass, which is 5.7, plus 40 grams, which is the same thing as 0.040 kilograms. We need to be consistent because I'm adding kilograms to kilograms, times of initial velocity, which is just 0 because you're holding the gun still. And so the total momentum before the collision is 0. That means the total momentum after the collision must also be 0. Now, how can I add two things together and have the total momentum equal 0? Well, the only way to do that is if one of those numbers is negative. In this case, the gun is going to go backwards, and so it'll have a negative velocity and therefore negative momentum. Let's calculate it then. After the collision, the gun is got a mass of 5.7 kilograms, and its velocity is unknown, traveling backwards. And the bullet has a mass of 0.40 kilograms and a speed of 640. That's a total momentum of 640 times 0.04, or 25.6. If we subtract 25.6 from both sides, and then divide both sides by 5.7, it's a little messy here. Let me rewrite it. Negative 25.6 over 5.7. That gives a velocity of the gun coming back of about 4.5 meters per second. Remember that that is roughly doubled, or about 9 or 10 miles per hour. That can hurt. Now, I've never shot a gun myself, but I've heard that you usually try to hold the rifle so that it's not out in front of you, but you kind of wedge it in against your shoulder. What that allows you to do is to combine your mass with the mass of the gun so that it doesn't recoil back as quickly. Let's quickly recalculate with the situation if you've got a 70 kilogram hunter holding the rifle so that the hunter's mass and the rifle's mass are all combined together. Actually, all that changes in this problem compared to the last example is that after the collision we don't have just 5.7, but we have the mass of the hunter plus the mass of the rifle moving off together at some unknown velocity, added to the momentum of the bullet, which is 0.040 times 640 still. That's still going to be 25.6. And the total mass is 75.7 now instead of just 5.7. If I subtract 25.6 from both sides and divide now by 75.7 instead of 5.7, we find that the rifle and the hunter move back now at only a fraction of a meter per second, or roughly 0.34 meters per second. That's much more manageable.